Okay, so we're going to finish up the last little bit of the questions I assigned for CP Opportunity. And then I'll upload this to YouTube and put an announcement on Canvas, so you'll have that for you. So the first one is, based on formal charge considerations, which of the following would likely to be the correct structure of atoms in sulfur dioxide? And we have two different arrangements, either a sulfur at the center or oxygen at the center. Both oxygen and sulfur want 6 valence electrons. I have 3, which gives me 18 total. You should know by now, hopefully from the lab, that oxygen that is neutral, which these are going to be double bonded. So that's still going to be true about the structure here. I have 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay? So there's going to be 18 all the way around. If I'm looking at valence electrons, I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Because the arrangements are the same over here, except for who is outer and inner, there are also 6 valence electrons on each side. Because there are 6 in, 6 out, this tells me that the formal charge on all the atoms is 0. So formal charge consideration says there's really no difference between these two structures. The difference, though, is if we think about the periodic table, oxygen is a second row element and sulfur is a third row element, and only third row and lower tend to be hypervalent, which means that the correct structure is going to be with sulfur at the center and oxygens on the peripheral. The next one on here was bond enthalpy. So in order to do this, I have to draw the structures. On the test, I would give you the structures for the reaction. On sapling, they would give you on sapling you might have to draw them. On the final exam, they would give you the structures. But it's good practice for drawing Lewis structures, and every little bit helps when you're preparing for your test. Okay, so if we think of making and breaking, I'm going to make these bonds, and I'm going to break all of these. Okay, so when I look at the math, that's going to be 2 molecules of C2H6. Each is going to have 6 CH bonds that need to break, plus in the 2 molecules I also need to break 1 carbon-carbon bond. I'm going to add that to the 7 oxygen double bonds, which leads to 4 molecules of CO2, each which have 2 carbon-oxygen double bonds, and then 6 molecules of water, each which have 2 OH bonds. Okay? And so now it's just a matter of plugging in my enthalpy values from the back of the book. I'm going to have 12 carbon-hydrogen bonds to break, and each are 415 kilojoules. And I'm going to have 2 carbon-carbons, which are 345 kilojoules per mole. And I'm going to have 7 oxygen double bonds, which are 198 kilojoules per mole. I'm going to add that all up together, and then I'm going to subtract from that 8 carbon-oxygen double bonds, which are 741 kilojoules per mole, and 12 oxygen-hydrogen bonds, which are 464 kilojoules per mole. Okay. So, to do the math on that, we're going to take 12 times 415 plus 2 times 345 plus 7 times 198 equals 7,056 kilojoules. And we're going to subtract from that what you can imagine is going to be a much bigger number, 8 times 741 plus 12 times 464. So that's going to be a big, oh shoot, I just canceled that whole thing out on my phone. That's why you don't do calculations on your phone. Okay, so they're both big energy makers, making a carbon-oxygen bond and double bond and making an oxygen-hydrogen bond. So when I subtract that, you should get 4,440 kilojoules negative, which, if we think about the type of reaction this is a combustion reaction. Combustion reactions are associated with the production of a lot of heat, and a negative enthalpy value suggests the same. Alright, so on to lesson 26. Okay, so in lesson 26, I left you with 2 Lewis structures and then the polar question at the bottom. Okay, so silicon with 5 fluorides. The negative charge usually exists on the central atom, in this case that's silicon. Because silicon wants 4 bonds, the negative charge essentially means that I'm giving it 5, which matches up really well with the fact that I have 5 fluorines. Okay, so the structure is going to look like this. Because there's no lone pairs on the central atom, there is a negative charge, but not a lone pair. The EP and the molecular geometries are the same. It's 5 coordinate, has 5 things coordinated, which makes it trigonal by pyramid. Beryllium with 2 chlorines. Beryllium wants to be 2 coordinate. So it's a super easy, straightforward structure. Because there's no lone pairs on the beryllium, the electron pair and molecular geometries are the same, which is linear. Alright, PCl4, the negative charge is probably going to be on the phosphorus. Phosphorus wants 5. If it has a negative charge, that means it has 6, 4 of which must be bonds, which means the other one must be a lone pair. So it's going to look like this. Go ahead and draw in our dashes and wedges so we can very clearly see our structure. The EP here is going to be trigonal by pyramid, but the molecular geometry is going to be seesaw. It's going to have polar bonds. Remember, they are going to point towards the more electronegative element, which in this case is the chlorine. So, yes, polar bonds. After you shower, go. Now, when I'm thinking about whether or not this is a polar molecule, I have to look at the arrows. So one arrow points this way to the right, and the other one's pointing in the exact opposite direction. So if you imagine pulling on the ends of a seesaw, they would cancel each other out as long as you were pulling equally in opposite directions. The ones that are not going to cancel each other out are these arrows pointing down. In order to cancel out the arrows pointing down, you would have to have something up here to cancel it out. That kind of looks like a breast cancer awareness ribbon. Anyways, you would have to have something up there in that upper area where the lone pair is to cancel it out. But we just have a lone pair, and lone pairs cannot cancel out dipole moments. So, therefore, this molecule is polar. Polar molecule. Okay? Because there isn't anything in this upper area to cancel out the dipole moment down here. Alright, next one is tin chloride. Negative charge is going to be on the tin. Tin wants 4 electrons. It's going to have 5 because 3 of them are bonds, which means 1 is going to be a lone pair. So it's going to look like this. Now in this case, all of the arrows are going to point down. Let's go back. The electron pair geometry is tetrahedral because there's 3 bonds and a lone pair, but the molecular geometry is going to be trigonal pyramid. Okay, so this is the molecular. right, polar bonds. Yes, the bonds are polar, and they are pointing towards the chlorines. Okay? Now, like the example above, in order for the green arrows to be canceled out, there would have to be something in that yellow area, a bond with another chlorine to cancel it out. But there's not, which means there's an unbalanced pull on the tin towards the chlorines. Okay? So not only does this have polar bonds, it is also a polar molecule. Okay? So imagine you had a tripod, okay? And you had people pulling, I guess I should draw them attached to them. You had people pulling the different legs of the tripod. Okay? And they're all pulling in this direction. Okay? Well, the tripod itself is also going to move in that direction because there's no one pulling it back this way. Okay? But if you had a rope and someone was pulling in the exact opposite direction, well, the rope itself is not going to move if they're both equal in strength. Okay, so we're talking about people equal in strength, not Goliath and David. Okay, so we're talking about equally matched atoms. So in this case, there's not an equal match. Bromine with 4 chlorines. Bromine wants to have 7 valence electrons, 4 of which are bonds, which tells me that the other 3 plus the 1 electron must be lone pairs. So remember, you have to get pretty quick at these structures. Alright, so electron pair geometry would be octahedral. 4 bonds, 2 lone pairs is 6, which is octahedral. But the actual molecular geometry is square planar. Remember, because it looks like it makes a square in the plane. Alright, so polar bonds, well, it's kind of hard to tell because these guys are neighbors. But for just the sake of this, we're going to pretend that they are different enough to make the bonds polar. Okay? But when we start looking at whether or not there is going to be a dipole moment, we have one arrow pointing this way, and then 180 degrees perfectly apart, there is another arrow pointing out the other direction. So it's like the tug of war. Now, the other option is the other 2 bonds. We have one pointing this way and one pointing that way. Again, 180 degrees apart, just like the tug of war. Meaning, the pinks and the yellows are going to cancel each other out. And this molecule is not polar. Not polar, okay? Next one, ICl3. Iodine wants to have 7 valence electrons. In this case, it's going to have 3 bonds, which tells me that the other 4 lone pairs are going to be are going to be lone pairs on the iodine. I'm losing my train of thought. Okay. Okay, another way you can draw it so it looks like your table. If you want to do that, I'm fine with that as well. Okay, so in this case, the electron pair geometry is trigonal bipyramid, but the molecular geometry is trigonal planar. Thinking about the tug of war, they are all perfectly 120 degrees apart in the plane. So if you imagined having a 3-way tug of war, person's got long arms, and everyone was pulling in the opposite direction equally, there's going to be no movement of the center of the tug of war because they're all pulling in opposite directions. So in this case, even though, yes, the bonds are polar towards the chlorine, and it doesn't always go towards the outside, it just is the case here, but in this trigonal planar structure, the bonds are polar, but the molecule is not. And that's supposed to be a check. It's not getting any better. Start over. Check for the bonds. Okay? So one of the things we talked about with polarity here was that it tended to be, the requirement was an electron pair on the central atom, but there are some exceptions, except when the structure is linear, square planar, or trigonal planar. Okay? Because in these three structures, even though there is a lone pair, the fact that they're all in the plane, they cancel each other out. Alright, this would be a good practice, and you know what? Your table will tell you this answer. Okay? So that's all of the questions I assigned you for CP opportunity. So you should have everything filled out, and you should be ready to start the next lesson with Dr. Spencer on Friday. Okay, bye.